Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In my discussion today, I'm going to look at the concept of an ideal gas of diatomic molecules. And this basically is going to be biased on the way of representing the diatomic molecules characteristics or properties in terms of the partition function. In our previous videos, we have been concentrating on the concept of statistical mechanics of atoms. And of course, this is going to be creating a ground for us in trying to consider another case for a diatomic molecule in terms of partition function. Now, from my previous videos, I mentioned that basically we're going to represent the partition function in terms of this specific notation, which is going to be given in terms of Q given as such. And this is going to represent all the thermally accessible energy levels at a given temperature. And therefore, as I said, of course, these specific properties can be used, or a property of a partition function can be used to represent key thermodynamic quantities which can be expressed in terms of a partition function. And generally, we are given this specific notation for a representation of a partition function of the specific, of course, levels, which, of course, as I've said, constitute all the levels. And this is going to be given in terms of the exponent of the negative value of internal energy divided by the value of kBt. Now, in this case, I had mentioned that we're going to write this one using a brevity, which, of course, was given in terms of beta, whereby beta represented 1 over the product over kBt. And in this case, we have decided that basically this is going to represent Boltzmann's constant, which, of course, is going to be a constant we come across in some of our discussions, especially on the concept of thermochemistry or physics. Now, in this case, this partition function is going to assist us in trying to describe the various properties of a diatomic molecule. And of course, we're going to see how they are going to differ from this specific concept of a monoatomic molecule. So in this case, I'm going to have this partition function represented as the summation between the first and all other energy levels, of course, all the thermally accessible energy levels, and we're going to have this one as an exponent of negative this internal energy, and we're going to have therefore this specific representation for the function of that negative b ui given as such. So this is going to represent this specific illustration for 1 over kBt given as such. So this is a general case for a partition function. And in this particular discussion now, we're going to look at the concept of diatomic molecules. And we are going to consider the degrees of freedom, which we have mentioned, of course, for a diatomic molecule. And in this case, I had mentioned that we're going to look at the 6 degrees of freedom for a diatomic molecule, which, of course, these are going to be the degrees of freedom. And I said that for a diatomic molecule, it's going to consist of 3 translational degrees of freedom, or translation degrees of freedom. And of course, we're going to have 2 rotational degrees of freedom. And then lastly, we're going to have 1 vibrational degrees of freedom for a diatomic molecule in this particular case. Now, in our discussion for today, in considering the diatomic molecules in terms of partition function, we're going to look at the rotational and the vibrational component of this specific diatomic molecule, so that we can see what ways in which we can represent these specific properties in terms of diatomic or partition function. So we're going to look at the rotational partition function, which is going to be given in terms of this specific, of course, degrees which I've mentioned. And of course, these are going to be 2 degrees. Now, in my illustration, I'm going to consider the case of a heteronuclear diatomic molecule, which basically consists of 2 distinct atoms, which are going to be perhaps illustrated using this specific form. And I'm going to consider basically some of the properties which are going to be used in trying to describe the rotational properties of this basic molecule. And these are going to be the components of the moment of inertia and the distance from the center of mass. Now, in this case, if we have such a kind of molecule, we're going to see that the bond length is going to be given in terms of the distance between these specific 2 centers. And we're going to have the center of mass basically being situated at a particular point in this distance between the two, of course, heteronuclear or the heteronuclear atoms which I've illustrated. And we can give the specific masses of these specific atoms which are forming this diatomic molecule given as M1 and M2. And I've said that the rotational properties of such a kind of an arrangement can be described using two specific aspects. And the first one, which I've said, is the moment of inertia and the distance from the center of mass. Now, in this case, from our mechanics, of course, given the specific description for the moment of inertia, which basically can be given in terms of I. So this is going to represent the moment of inertia. So for us to describe the moment of inertia of this specific kind of an arrangement for a heteronuclear diatomic molecule, we're going to consider the summation of its specific component of the masses which we have given. So this is going to be a range of course, determination from the first to the n, which we're going to see. Now, I talked about the concept of ideal gas of monoatomic molecules, where I explained the component of n. So these are going to be the summation of the masses, ith masses, and of course the bond length, which of course is going to be given in terms of r. So in this case, this is going to be a formula for description of the moment of inertia of such a kind of a system. And of course, it's going to assist us in trying to describe some of its properties insofar as the rotational partition function is concerned. Now, in this case, talking about the component of mass, we're going to use the concept of a reduced mass, which is given in terms of this specific notation, whereby the reduced mass of this specific kind of course, an arrangement can be given in terms of the product of the two masses, which is M1, M2 over the sum of these two masses given as such, as we have been describing the moment, or rather the reduced mass from description of the moment of inertia from our discussion of various topics under the concept of a classical, perhaps mechanics. Now, in this case, we're going to look at the concept of describing this specific molecule in terms of allowed rotational energies. And we're going to use the concept of Schrodinger's equation in trying to find the solution for energies, of course, which is allowed rotational energies of this specific set of a molecule. And this, of course, is going to be achieved using the Schrodinger's equation. Now, in this case, this equation is going to be given in terms of this internal energy, which is Uj. And of course, this is going to be a rotational energy given in terms of Bj into J plus 1. Now, in this case, I'm going to mention about the concept of degeneracies, which of course are going to be specific aspects of energies, which are going to be the same types of energies. Now, in our description about the concept of finding a particle in a box, I mentioned basically this is specific components which I'm going to give in terms of nx, which represented various components of the quantum numbers being described, of course, in this specific case. And these quantum numbers, of course, were the numbers which represented the various energy levels. And in this case, for a three-dimensional box, we have said that these are going to be nx, ny, and z. And of course, these are going to contain the same energies, but of course, as we can see, they're going to be for the different Cartesian components. Now, this one can be referred to as degeneracies, which are going to be having the same energies. Now, the element of J, which I've given from this Schrodinger's equation, therefore, is going to represent various degeneracies. And we can give this specific Schrodinger's equation meaning by trying to have this particular component of B, which is a rotational, of course, which is going to form a rotational constant. And this rotational constant is a ratio between the square of Planck's constant and, of course, we're going to see that it's the square of Planck's constant and the product of 8 pi times the moment of inertia, which we have obtained from this. So we're going to use this specific rotational constant in trying to describe the energy of this particular atomic molecule, given by basically the equation of the Schrodinger's equation, which we have given as this specific point. So we're going also to see that the component of J, which I've given in that specific equation, This is going to represent the rotational quantum number. Now, this rotational quantum number is going to represent the degeneracies, as we are going to see later. Basically, where the value of J is equivalent to 2. So this is going to be the value of degeneracies being represented basically for G is equivalent to 2J plus 1. And this is going to be the same energy levels or the similar energies which are going to be represented in terms of degeneracies. Perhaps this is going to be more clearer for us whenever we're going to talk about the concept of rotational energy levels for a diatomic molecule. And I'm going to use a specific representation in trying to give that a specific representation. Now, in this first part, of course, I'd like us to, take note of this specific representation. And this is, of course, the concept of the Schrodinger's equation in trying to describe the allowed energies of this rotational component of course, a freely rotating molecule. Now, in our second discussion, I'm going to look at a specific aspect of these particular energies. And of course, we're going to look at a final way of trying to express this partition function in terms of the rotational contribution. We're going to consider some of the several factors which are going to be included. Of course, which we're going to check whether that molecule is going to exhibit either classical or rather quantum behavior in that particular case. So kindly check our description boxes for various links of other videos, and also check our next video, which we're going to look at the specific additional properties which I've mentioned, and those together with others are going to assist us in trying to describe the characteristic of an ideal gas of diatomic molecule in terms of the partition function. So that is it for now, guys. By God bless you. Catch us in our next video.